Should we start now?
Yeah, sure. Yeah, we can get started. It's 11 o'clock ADT. Okay. Yeah. Good
Okay, I'm
morning.
resuming the record. This one. I'm resuming the
Yes.
record now.
Sure, sure.
Okay, go ahead.
Yeah. Thank you, Priyank. Yeah. Yeah. Good morning, everyone. Thank you for joining today Optical Sensors Clusters monthly webinar series. So this is webinar 6 on quantum sensor for non-invasive monitoring for cerebral oxygen metabolism. Yeah, thank you for joining. So we are great to have expert speaker, Dr. Mamadou Diop. So I'm gonna read his bio. So Dr. Mamadou Diop is a medical biophysics undergraduate chair and an associate professor in the Department of Medical Biophysics and Biomedical Engineering at Western University, located in Ontario, Canada. He leads the Translational Biophotonics Lab, and he is also a principal investigator in the imaging division of the Lawson Research Institute at St. Joseph's Healthcare, London. So Dr. Diop and his BSc in physics from Dakar University in Senegal and completed his PhD in physics at Laval University in Quebec, where he investigated colloidal photonics crystals. So he then pursued postdoctoral training at the National Research Council of Canada in Ottawa, focusing on optical trapping of all living cells. So his research is centered on the development and clinical translation of non-invasive optical technologies for point-of-care hemodynamic monitoring, with particular emphasis on neuromonitoring and early detection of sepsis. So his lab specialization in time-resolved near-infrared spectroscopy, diffuse correlation spectroscopy, and hyperspectral tissue spectroscopy, aiming to quantify key physiological parameters such as cerebral blood flow, oxygen metabolism, and tissue perfusion in real time. So thank you, Dr. Mamadou Diop. Yeah, so at the end of the presentation, you can post your question in the chat box, or feel free to unmute yourself and then ask any questions. Yeah, thank you. Thank you. Please go ahead, Mamadou.
Thank you very much for that introduction, Nagesh. So I'm going to start with a reminder of why it's important to monitor cerebral metabolism. So several studies going back in the late 70s have shown that when the cerebral blood flow decreases, because normal cerebral blood flow is around 50 millimeter of blood per 100 gram of brain tissue per minute. Now, if the blood flow decreases below 40, you start to be in the region where you have oligemia. Now, if the blood flow drop below 20, that's where you start to have electrical function. The electrical function going to start to be disturbed, and you have release of potassium and cell death. And the numbers here are between 15 and 25 milliliter of blood per 100 gram of tissue per minute. You start to have electrical failure. And below 15 units, you start to have membrane failure and death. And this is also linked to what's happened in the metabolism. Because when the blood flow decreases below certain threshold, the metabolism going to start to follow. What I have here, CMR2, we're going to see it in the next slide, stand for the cerebral metabolic rate of oxygen. And when the cerebral metabolic rate of oxygen drop below 1.3 units, that leads to an infarction. Then these two information, what they're saying is that cerebral blood flow and metabolism are very sensitive biomarkers of brain health. Now, to illustrate this, this is a result from an experiment that we run a few years ago used and this was done in an animal model of neonate. And what we're showing here is that on the y-axis, what you have here is the cerebral metabolic rate for oxygen, and on the x-axis, you have the cerebral blood flow. And what this is showing that when cerebral blood flow decreases, this is a relative measure, so 1 here stands for 100% for the baseline. When cerebral blood flow starts to decrease, the cerebral metabolism remain constant. And up to a certain point, now you see the cerebral metabolism start to depend linearly on the decrease in cerebral blood flow. And in this case, this is between 60 and 70% of the initial cerebral blood flow. And this is a dangerous region where you don't want to be. Now, there is a linear relationship between the cerebral metabolic rate of oxygen and the cerebral blood flow. In this relationship, as again, the CMR2 is the cerebral metabolic rate of oxygen, which is the amount of oxygen consumed by the brain. And why this is important? Because the brain is only about 2% of this total body mass, but it consumes 20% of the oxygen consumed in the body is consumed by the brain. And the brain is the organ that is the most sensitive to ischemia. If you have a stoppage of cerebral blood flow, then immediately you're going to have an infarction. So CBF is cerebral metabolic rate of oxygen. You see, this is the Fick principle. The cerebral metabolic rate of oxygen is equal to the cerebral blood flow multiplied by the difference between the arterial blood oxygenation and the venous blood oxygenation multiplied by this Ca here, which is just the constant that reflect the oxygen carrying capacity of the blood. So, but however, in this way, this is the way that cerebral metabolic rate of oxygen is measured using MRI, using PET, and using optical technology, which is going to be the focus of my work. Now, there is an assumption that is built in this equation here. This is the Fick principle. It only applies when you have steady state condition, not when things are very dynamic. And the other assumption is that this, to assess the venous oxygen saturation, you have to assume an arterial venous ratio, which is typically about 75%. Now, but in certain conditions that may vary and that will affect the accuracy or the reliability of the measuring the metabolic rate of oxygen using this formula. Now, in optics, when you use optical spectroscopy, there is another way of estimating the metabolic rate of oxygen in the brain. This is by monitoring the redox state of cytochrome C oxidase. So what is cytochrome C oxidase? Cytochrome C oxidase is an enzyme that sits in the inner membrane of the mitochondria. And it's part of the electron transport chain, which starts with complex 1, go from complex 1, 2, 3, and 4. And complex 4, which is the last complex, is cytochrome C oxidase. And you receive an electron through the electron transport chain to reduce oxygen into water. And this process here is what consumes more than 90% of the oxygen consumed in our body is consumed through this reaction. And you can start to see that cytochrome C oxidase is necessary for oxidative metabolism, okay? And this oxidative metabolism is what drives the synthesis of ATPs, because anytime you have an electron passing through the electron transport chain, you have pumping of proton into the intermembrane space, and these protons pulling into the intermembrane space are used by ATP synthase, which is this machine here that synthesizes ATP. So, and ATP is the main fuel used by living cells. So this is the process of generating energy in tissue and in living tissue, especially for eukaryotic cell, which is like the cell that we have in our body. And so cytochrome C oxidase is necessary for oxidative metabolism. It drives the ITP synthesis, as I just mentioned, and by monitoring it, that provide a direct measure of oxygen consumption, of oxygen metabolism. So then you will ask yourself, well, then if this is the case, why is not cytochrome C oxidase used all the time to monitor oxygen metabolism? Because it provides a direct measure of oxygen metabolism. Well, it's because measuring cytochrome C oxidase is very challenging. Optics is the only technique that I know that can do this. And when you do this using optical spectroscopy, there are challenges there. First, let's look at here. This is these are the absorption coefficient of the main light absorber in tissue when you do optical spectroscopy. You have here deoxyhemoglobin, oxyhemoglobin in red, and water in green. And the other two chromophore is fat, which is this purple curve here. And then you have cytochrome C, oxygenated cytochrome C, and reduced cytochrome C. And if you look at in this wavelength range that interests us, which is between 700 and 800 nanometers, you will notice that two things. The absorption coefficient of blood is much higher. It's at least an order of magnitude higher than the absorption of cytochrome C. You can see the absorption, the red and blue curve in this curve here, in this figure here, are very small. And you can see the extension coefficient here are much smaller than the extension coefficient of blood. And on top of that, there are broad spectra that has no features. And to summarize that, so if we take the difference between oxidized and reduced cytochrome, we obtain this curve here. That's the curve that we're going to be using. And what you notice is that this is a broad spectrum and has no feature. And on top of that, the concentration, the absorption of cytochrome is about 10% of the absorption of blood. So this is what makes measuring cytochrome C oxidase very challenging. Now, our group and other group have developed techniques that allow us to measure this, and that is using a very simple technology where you have a halogen lamp then that emits, it's just basically a white light source that emits light that is now coupled into an optical fiber, goes into the phantom or the subject, and the light is scattered inside the tissue and picked up by another optical fiber and send it here to a very simple spectrometer. Now, so this is the basic principle. And now what we did is we built a device that includes that spectrometer and light source. We also built another technology I'm not going to be talking about here, which is called diffuse correlation spectroscopy, that allow us to measure blood flow. And the optical fiber that comes out of this device are very simple. This is this optical probe, and this is a probe holder that you put as a strap on the head, and the fibers come and slide into the hole. This optical fiber, there is a notch here. Your probe slides in and sits there. And this is an example of the fiber used in a neonate. So the fiber comes in. You see the probe holder is now strapped around the head, and the fibers just slide into the notches here and stay there and supported by the grip. So before we went to do a study on neonate, we used an animal model of neonate, which is a piglet model in which we induce ischemia, hypoxia ischemia. In the yellow curve here, show the period where we have ischemia, where we clamp the carotid, artery, and in the second part here is when we reduce the fraction of oxygen that is breathed by the animal to mimic what's happened during hypoxia ischemia, which is a condition where an infant is at birth. An infant is typically the umbilical cord will wrap around the neck, and these are sometimes called blue babies, And this is a very severe condition, which that's what we are mimicking in this animal model. And basically what you see is that the green curve here is the cytochrome C oxidase, and the blue curve here is the oxygen saturation, and the black curve is the blood flow monitoring. And we can see when we use for the control animal where we did not induce this hypoxia ischemia, you see the curves are all flat, but during the hypoxemia, especially during the ischemic and the hypoxic period, you have a significant drop in flow and drop in the metabolism, and then it recover after that. So this was a necessary step to validate our technology. Now, after that, we move to neonate. So this is the example I'm going to be showing is this infant here is not one of our subjects, and information that I got from the web. But this baby here is one of our subjects. And here one of my colleagues, a neurosurgeon, is coming in. And because this infant, they have a condition called hydrocephalus, which is an accumulation of cerebrospinal fluid into the brain. And once you have that, so the ventricle expand, and this case is an extreme case, but even in our subject here, you see the neurosurgeon will come in and place a needle into the ventricle and have a probe there, so that will allow them to drain the cerebrospinal fluid from the ventricle to reduce the pressure in the brain. And we start monitoring during that period. And this is the period, this period here in the shaded region here at the beginning is baseline before they start draining the cerebrospinal fluid, and this is the period afterward. And this at the end of this VT here is when the ventricular tap is ended. So it's the beginning of the ventricular tap, which is inserting the probe into the brain and draining the cerebrospinal fluid. And what you can see here is the cytochrome C oxidase increases after the ventricular tap. It's telling us that this infant brain was squeezed, and that the ventricular tap has relieved that pressure, and now you see an increase in metabolism. So we have also taken this device, and we have done monitoring during cardiopulmonary bypass in adult. And again, similar to what we have seen in the early example that I saw, when cerebral blood flow decreases, this is the baseline, and now you have a decrease in cerebral blood flow here, and up to some point, the metabolism remains constant. This is now shown with cytochrome C. The previous example I was shown was for CMR2, cerebral metabolic rate of oxygen. And similar trend, after a certain period, after a certain limit, you start to have now a linear correlation between cerebral metabolism and blood flow, which is the dangerous region. And you can see in this case, this is happening. In the previous case, it was happening between 60 and 70% of the baseline, but in this case, it's happening between 70 and 75% of the baseline. However, because this was an adult, adult patient undergoing cardiac surgery, we believe that the reason of this difference here is that it's because we have a significant contamination of the signal by the thick adult extracerebral layer. What do I mean by that? If you send light into tissue, this is a light will come here from the source, and you have your detector here. This is an illustration of the optical path in the tissue. Okay, so most of the light will be propagating on this darker region, which basically is the extracerebral layer, which is the scalp and skull. And a few photons will propagate inside, get right into the brain if you have an adult. In infant, it's not a problem because their skin and scalp are very thin, and the light will just this part of the signal will be mostly in the brain. Now, how do we manage this? Well, if you do a simulation, you will notice that the photon, if you can have a technology that allows you to look at the photons as they fly into the tissue, you will notice that the photon that you detect later will have a path that's similar to the blue path here. So these photons, they have a very high probability of propagating in the tissue and getting into the brain. And how can you do that? So you can do that by using a technique that's called time-resolved spectroscopy. In this technique, you use a pulse of light, and you send the pulse of light into tissue, and you can see it in the simulation here. You send at the beginning, you have just a pulse, and over time, the light just propagates into the tissue. If you use a technique that allows you to distinguish the photon, you can see the photon that you detect late in the tail of your detection curve. Those photons have a very high probability of probing the brain. But to do this, you need light sources that has very high repetition rate, narrow bandwidth. You need single photon detectors that are sensitive, and you need excellent timing. You need to have also a detection system that has very timing, resolution, and accuracy. This is a schematic of a setup where we have the light source and the optical fibers are guided from the light source to the head. This can be an animal or phantom or a human, and light will propagate inside the tissue, and some of the light will be detected, and you guide it with an optical fiber and go to your detector. So the light sources can be pulsate photodiode, you can have supercontinuum laser, or this titanium sapphire lasers. For the detection system, it has two parts. You have the detector and the timing electronics. Due to the high scattering of light in tissue, the intensity measured at any given point in the surface is very weak, and that's why you need very sensitive detector here. You can use photomultiplier tubes. This one is a regular PMT. This is a PMT with cooling and hybrid PMT that provide better temporal characteristic. You can use spot arrays on APDs. And for the detection, you can use any TCSPC, time-correlated single photon counting detection system, in order to capture the time of flight of photon inside the tissue. Now, this is very interesting, but keep in mind, if you want to do now cytochrome C oxidase, so this technique allows you, this time resolved technique allows you to increase your sensitivity to the brain. But keep in mind, if you want to measure cytochrome C oxidase, you need to do this, but for a broad range of wavelengths, so for a broad spectrum. And because of that, you need a hyperspectral technique, okay? So people have tried to do this in the past, and what they have here, this is a paper that was published about 10 years ago. You have your supercontinuum light source, so you send them here into a grating or a prism that allow you to disperse the wavelength you have. And then you have here an adjustable slit that allows you to select a specific wavelength. And then you scan. This is basically a wavelet scanning, and the light go to your sample and you detect your light. And then for every single wavelength, you measure wavelength by wavelength. You can imagine this is a very slow process. And to tackle this issue, we come up with the idea of taking a different approach. And our approach is that we use a supercontinuum laser, which is a pulsate laser, but have a broad spectral emission. We just filter a part of the laser that we are interested, which is in between 600 and 900 nanometers. We focus using these filters, we focus the light into the fiber, and we send the light into a grating. So the grating will disperse the light into its wavelength component. And instead of now selecting every single wavelength, we send all the wavelength into this digital micromirror device, this DMD here. So the digital micromirror device, now we're using this digital micromirror device now to do what's a technique that's called compressive sensing. I can answer a question about that later. And basically what we do is, this is a picture of the digital micromirror device. You see here, it's showing some of the stripes are dark, some of them are bright. And we use that to, what we do with this is that we use this to select every single pixel of this digital micromirror device can be addressed. So we use, because our wavelengths are similar on the wavelength range, because the grating is just dispersing the light on the x-axis. So we, in this case, for instance, if you wanted to just do a wavelength scanning, we can only enable one row and everything else will be dark, so that we can send the light into the sample through this optical fiber. And then you go to the next wavelength, third, and so on until the end. But if you do that, it becomes slow. Basically, what we do, we show some mask that allow us to send some of the light into the sample, and some of the light would send it away from the sample. And if we use this technique, we can reduce the sampling rate going from 120 seconds to something around 66 seconds. So that's a significant decrease in sampling rate. And then once the light comes into the sample or the human, the light will be scattered and then picked by its optical fiber and sent to our detector system and our timing correlation here. So this is how it looks. This is when you build the entire system, this is how it looks. And in this case, we added a regular spectrometer, which is sitting here, and a regular light source, so halogen lamp, so that we can compare, and you will see that in the coming slide, we can compare the performance of our hyperspectral time-resolved system and the regular time-resolved system. In this kind of specific example here, what you see here, where I'm pointing with my laser pointer, this is the detection, the photon counting system. So our detector here is an array detector. It has an 8x8. It's a SPAD array. It's a SPAD quantum sensor. It has an 8x8 array. And this is the dark noise of the detector. And this is the quantum efficiency, and you can see the quantum efficiency drops when you get close to 9 seconds. And this is a single instrument response function measured with this device. So because we have an 8x8, we have 64 channels. And what we do, basically, we use all these detectors. We send all the light to all these detectors. We scramble it and send it here. And we use this to increase our sampling rate so that we can acquire our photon at a pace that is higher than 5% of the laser repetition rate without having problem of pileup effects. I can answer a question about that later if anybody has a question regarding that. And if you do that, all of this, so basically you are able to generate a curve that looks like this one. So basically, what we have here on this axis here, we have the time of flight that is measured by our device, and on this other axis here, you have the wavelength. So this curve is showing here that we can capture both the time of flight of the photon and the wavelength component. We can capture time and wavelength, both the spectral information and the temporal information of the light source of the signal that has propagated inside the sample, and we are detecting. Now, what you keep in mind that this curve here has been captured for less than 6 seconds, and that's going from 120 seconds to 6 seconds is a huge improvement, and now allow us to envision using this technique for neuromonitoring. Because, when you have the blood flow, when the blood flow decreases to those levels that I was mentioning at the beginning, if you don't measure that very quickly, if you are sampling only every 2 minutes, you may miss that, or you may have an infarct without detecting it. So by sampling very fast, you allow yourself to be able to monitor those at a very high sampling rate so that if there is an influx or decrease in metabolism significantly, you can detect it. We also investigated the spectral resolution of the device. And what we are comparing here is the blue curve here is what you get when you use a regular spectrometer, commercial spectrometer, very high spectral resolution. And the red curve is the resolution of the hyperspectral time resolved system we developed. You can see the resolution is lower than this high resolution commercial unit, which has a resolution of about 1 nanometer. But our resolution, it was about 6 nanometer, which is more than what we need for capturing reliably capturing the spectra of oxyhemoglobin, deoxyhemoglobin, and cytochrome C oxidase. Now, after we build the device, we move to now the first step of our after the characterization, we move to a first step of our validation, which was a tissue mimicking phantom experiment. In this tissue mimicking phantom, what we did is, this is a 2-layer phantom. This opening here, this is the bottom layer that mimics the brain. We put the probe directly on the bottom layer. This is the probe of this continuous wave, it's the regular spectrometer. We put it directly on the brain, on the bottom layer. And now we have a top layer that sits on top of what's called the brain mimicking layer that mimics the scalp and skull. And we put our optical fiber from the time resolved spectrometer on the top. So now the time resolved has to go through all these brain extra layers that mimic the extracerebral layer to probe the brain. And if the time resolved provide good results, then that means that this technology is really good, because we are comparing it now to our ground truth, which is the measurement that we are acquiring directly on the bottom layer. And this curve here, there is a lot of information in this curve, but I'm going to try to walk you through it. So the dotted line here is the direct measurement acquired on the bottom layer for deoxyhemoglobin. And the dotted red line here, the dotted red curve here is the dashed red curve here is the oxyhemoglobin measured directly on the bottom layer using this part here. And this noisier curve here, the red one, is the oxyhemoglobin measured by the time resolved through the extracerebral layer to measure the bottom layer. And you can see they are very similar. This is oxyhemoglobin. And this dashed curve here, this yellowish curve, is for the cytochrome C, which is the metabolism. And you can see for the metabolism, we're doing extremely well. For the deoxyhemoglobin, we have some little bit of a discrepancy, but it's still extremely good compared to what you would have if you had a situation where you put both curves, which is the regular technique, the technique we had before, where you have the regular NIRS, which is the CW, continuous wave technique. You put it on the top layer and put this time resolve on the top layer, this is what you get. Now you see the dashed blue curve and the dashed red curve are what you measure with a regular NIRS on the top layer, and it's overly underestimating the real changes. So to summarize this is showing that our time resolve technique is much, much more sensitive than all the previous technique we had, which is this CW technique. And it's showing that we can measure the oxyhemoglobin with pretty good reliability. Deoxyhemoglobin is a little bit underestimated, but cytochrome C oxidase, measuring metabolism is pretty good with this technique. Now, that brings me to the end of my talk. So the key points here are the near-infrared spectroscopy can be used to measure cerebral metabolism in neonates. However, if you want to monitor cytochrome C oxidase, which is another very important biomarker, direct biomarker of cerebral oxidative metabolism, you need hyperspectral. You need dozens of wavelengths in order to do that. If you want to go to adult, when we use quantum sensing with time resolve, this extend now the use of hyperspectral near-infrared spectroscopy from neonate to adult allowing for adult neuromonitoring. I would like to finish by thanking my lab, all the trainees that has passed through my lab, all the current trainees, my collaborator, and all these generous source of funding from all these Canadian funding agencies. And I would like also to thank you for your attention, and I will be ready. I'll be happy to take any question.
Yeah, great. Yeah, thank you very much. Yeah, you guys did great work. Yeah, if you have any questions, yeah, please feel free to unmute yourself or post it into the chat box, please.
Hello, Dr. Diop.
Yeah.
So I had a question. On page 13, did you say that there's a connection between cerebral blood flow and metabolism?
Okay, let me see. Page 13.
Yes.
Yeah, here.
Yes, here.
Yeah, so yes, that's right. So in this case, we are monitoring metabolism using the changes in the cytochrome C oxidase. And you can see as the blood flow, so here, this is change in cerebral blood flow. Here you have 30% decrease, 40%, 50% decrease. And when blood flow decreases, the metabolism doesn't decrease, because this is called kind of oxygen, like the kind of a physiological reserve. Okay, the blood flow has to decrease below a certain threshold for metabolism start to decrease. And when you start to see metabolism changing linearly with flow, that's really the dangerous region. You are in a region where you can have you can have an infarct, because here you know that now your consumption is supply dependent, and you don't want that.
So could you use, I guess that's what you've done here. You can use cerebral blood flow to validate techniques that monitor cytochrome C oxidase, right?
Yeah, you can, well, not to validate it, but the point is when you measure both, you measure metabolism and flow, and you start to see a strong correlation between metabolism and flow, that is an indication that you likely have a problem.
I see.
Yeah.
Okay, thank you.
Thank you for the question.
Great. Yeah, any other questions? Yeah, if not, yeah, thank you very much. Yeah, Dr. Diop, very well constructed presentation. Yeah, appreciate your time. Thank you very much.
No problem.
Then,
Thank you very much, and have a good day, guys.
yeah, have a great weekend, all of you. Yeah, thank you. Bye-bye.
Okay, bye.